Section 5.2, we're going to take a look at multiplication and division of integers. We're going to do 3 of our 4 models that we had used before. They lend themselves very well to this argument, some better than others. And the first model we're going to see was that chip model. Okay, so let's take a look at how we do this. In order to use the chip model, we have to talk about notationally what each of these values mean. So this negative here is going to be removing. And again, we could do the negative and the -3 to be removing. But one of our negatives, if we have 2 present, is going to be removing. And the 4 is 4 groups. Okay, so remove 4 groups. Over here, it's going to be of 3 red chips. Negative is red, remember? Remove 3 red chips. Okay, so here's how we start with that. Start by drawing your circle. Don't get ahead of me and put anything in it yet, okay? Just draw your circle with nothing in it. This circle is 0 in it, correct? I can't take this circle and remove anything because there's nothing in it to remove. That sounds like an obvious statement, but are you good with me so far? Okay. In order to remove 4 groups of 3 red chips, I have to have 4 groups of 3 red chips, but if I just go putting in 4 groups of 3 red chips, that's not starting out at 0. We do, so that's exactly what we're going to do. We're going to put in 12 red chips and 12 black chips. And if we had put in, say, 15, it's okay. We'd just cancel out, 0 pairs later or whatever. So there's nothing special about the fact that we had to know how many to put in or anything like that. We don't. We're going to use our knowledge so that we can avoid having to have lots of simplification at the end. But we need 12 black and 12 red. Red, 12 black. This is still equal to 0, right? It may be your sort of favorite picture of the number 0, but it is. It's equal to 0. And now we can remove the 4 groups of 3 chips. So here's one of my groups, removed. Here's another one, removed. The third one removed, and here's my 4th one removed. So the answer at the end ends up having, oops, 12 black chips in a circle. And there you go. Negative times a negative equals a positive. It's pretty fancy. Now obviously the picture works almost identically when we've got the charged fields model. So draw yourself a circle. Again, we'll write out the language for this so that you have it in your notes. This says to remove 4 groups. If this 4 at the beginning were not negative, let's say it were positive, do you think we'd be removing? We'd be adding. And then do we have to put in 0 pairs to add things? Well, no, we'd just add 4 groups of 3 chips, right? We could do that. So it's the removing that's forcing us to put something in to begin with that didn't actually exist there before. And then this, of course, is 3 red chips. Oh, I'm sorry, not red chips. 3 negatives, right? 3 negative charges.
Dr. Haynes, what can I write as a note to the side of this example, what you just said about positive?
If you were doing this, we can do an example real quick. Let's say that this said 4 times -3. This would be adding 4 groups of 3 negatives. So in adding it, you don't have to worry about these 0 pairs. You just put in what it's telling you to put in. The problem is that because there's nothing in my circle to start with, the removing requires us to do something creative at the beginning. That is putting in these 12 black and 12 red chips to start. So on this one, I need, oops, get that again. I need 12 positive charges to balance out my initial need for 12 negatives. Because that's still 0. It's the picture of 0. Not supposed to be adding, it's supposed to be removing. So if I have a picture of 0, in order to remove, I've got to have stuff in there to remove. But it still needs to equal 0. And then I can remove my 4 groups of 3 negatives. I didn't get that one done right. Let's try that again. There we go. And my final diagram, I'm left with positives. All right, so I said, we were going to, because there's 2 negatives, I decided the first one was remove 4 groups of 3 negative charges. Could I have instead said that the -4 at the beginning is the 4 negative charges and the 3 at the end was removing 3 groups?
Yes.
Yeah, could I remove 3 groups of 4 negative charges? Sure. It would be the same thing. The picture would be slightly different, but the answer would be the same. We would just be doing it in a different order, and that would be fine. Let's do the number line model. This is probably my least favorite model for this, just to be honest with you. It's okay. It's just not very intuitive unless you have a word problem built around it. Okay, so this is not a very good justifying why in the world of positive, negative times negative is positive. It doesn't do a good job of that. But there are points in which it works a little bit better. The points in which it works a little bit better really have to do with there being sort of a value at the beginning that you're then, adding the -4 times -3 to. And you have a good example in your group work when you get there, and I'll kind of identify it for you when we get there. So we're going to put in 0 here, and I'm going to count out 12 to the right, okay? And then we're going to talk back about what the -4 and the -3 mean in terms of this model. All right, so this -4 means that we're going to move left, that's why it's negative, okay? 4 at a time. So that should sound okay to you. You're making jumps, you're making the jumps left, and you're doing the jumps 4 wide at a time. Okay? Yes?
Sorry, just for the sake of my brain.
Mm-hmm.
Would it be at this time when, if I had a student that had switched the negative and the positive signs, that I would say move right 4 at a time?
That would be tricky, right? Because then we're going to have a model that's not going to match up.
She would have to be aware of what's going on, so that's why
Yeah.
I have to really let her know that this is why, so that I'm not confusing.
Yeah, I think that would confuse things. You're right. Yeah. All right, the -3 is the part that's weird. Okay, and again, the -4, -3 ordering doesn't make any difference. So if we said that the -3 was move 3 left, or move left 3 at a time, we could do that. But one of the numbers going to be like this that I did for the 4. This one right here says that the time starts 3 blank ago. So like 3 hours, 3 minutes, whatever 3 time unit you want. I don't care what the time unit is. But it starts 3 whatever ago. 3 whatever in the past. And the question you're asking yourself is, where were we 3 whatever ago? I'll give you a word problem kind of visual for this as soon as we're done with this example. But, so the idea is that if I didn't have these numbers on the number line, let me just erase them, okay? And I'm supposed to be jumping 4 at a time left, right? I'm moving 4 at a time, and I'm doing it for 3 times. So this is here, there's my first jump 4. Here's my second jump 4. And here's my third jump 4. So without even any numbers on the number line kind of thing, okay? I made 4 jumps left, I made 3 jumps left 4 at a time. And basically the idea is that I end at 0. Wherever it is I started, I end at 0, and the question is, well then where did I start? And the answer is 12. Now you've done word problems along this line before. You wouldn't have recognized them as this and probably wouldn't think of it right now. But you think about something like this and you say, we'll do weight. Let's do like a scale measurement. I've lost 1 pound. No, one's not a good number. I don't want to use half numbers either because we haven't done decimals in here. Let's just say 2, just for the sake of doing it. I've lost 2 pounds a week for the last 4 weeks. Right? 2 pounds a week for the last 4 weeks. How much weight have I lost? Well, that's 8 pounds. We don't report it as -8, right? The fact that we use the word lost sort of means -8. But let's say it's something like this. I've lost 2 pounds per week for the last 4 weeks, and I started out weighing 150, and now I weigh 150 pounds. What did I start with? Well, what did I do with the 150? Well, we add 8 to it. You're doing something sort of in a back in time kind of thing. The example your book has is an example with enrollment numbers at a school, I think, or something like that. So you're looking at something where sort of like, how did it change? What would I do if I had to go back in time? And that's how this model works. Like I said, it's not my favorite model for explanation. It does work in some situations, like context situations, but this is what it looks like. All right, integer multiplication, a few facts. A and B are integers. If A is less than 0 and B is less than 0, then A times B, sorry, I guess I have to write this in for you now. A times B is equal to the absolute value of A times the absolute value of B. In other words, if I have 2 negative numbers and I multiply them, I can ignore the negatives. That's what this really just says, right? 2 numbers that I multiply that are negative. I really just need to know what the numbers are without the negatives, and that's going to be my answer. The second one says, if A is negative and B is positive, or A is positive and B is negative. So now the signs are switched. Okay, 1 positive, 1 negative. Then, if I multiply the 2 numbers together, again, what do I really do? Well, I have a negative, and I multiply the 2 numbers, whole number parts, together. -7 times -7 times 5. What do I do? Well, I kind of ignore the negative, don't I? And I just say, what's 7 times 5? It's 35, and then I put the negative back on in the end. Okay, it's a prior knowledge kind of thing is the reason why we do that. Okay, some properties of integers. You have seen many of these before, just like we did in the last section. The first one, closure property of integers. What does closure mean for multiplication? You multiply 2 integers, you get an integer, right? If you multiply 2 integers, you don't get a fraction, you don't get a radical, you don't get a decimal, you get an integer. So, what was that?
You can grab it out of the air.
You can grab it out of the air. That's right. So A times B is a unique integer. All right, what is the commutative property for multiplication? What's it say? Yes. A times B is equal to B times A. What's the associative property say? A times B times C, and this first 2 are grouped together, is equal to what? A times B times C grouped together like so. Looks good. All that's just like whole numbers, right? Identity property. We had this one before too. What is the identity element for multiplication? 1. Identity element is 1. The identity property then says that that number 1 is unique, and when you multiply, in this case it's a whole number, or this case it's an integer, last time it was a whole number, but when you multiply that by A, you get A. And of course 1 is the unique number that does that. Distributive property. I think we had this one before too. I don't think you'll see any difference here. A times B plus C is equal to what? Yeah, A times B plus A times C, or C times A, either way. Yeah. And not only that, but it works the other way too. If I had the B plus C on the left, and I multiplied it by A, I could get, and I'll keep it in order, but again, the order doesn't really matter. It's BA plus CA, or AB plus AC. And the last one we've seen before, what is the zero multiplication property? You multiply by 0, you get 0. So 0 times A is equal to A times 0. That almost looks like the identity property, but you don't get back the A that you started with, right? You get back 0 instead. Yeah. And 0 is unique. It is a unique value to do this. There's not any other numbers that have that property. All right, so what we're going to do is we'll do one more example and we'll call it quits for today. This is an example where we identify the property used. So write them down, take like 30 seconds to figure out which one you think is which for A through D, and then we'll make sure everybody has the same thing. I know some of you already have done this, but when you do have your all four written down, just put your pencil down so I can kind of keep track of who's still working. Thanks. Okay, I think we're pretty close. Out with the first one. What property is this? It's the closure property. If you'll remember, this symbol means is an element of, and your book uses I for integers, so is an element of the integers. What's the second property? This is the zero product property. What's the third one? Distributive. What's the fourth one? Commutative. I'm going to rewrite this word out because I want you guys to see that there's a couple of you who still don't know what this word looks like. It's commutative. Was that you, Lauren? Fabulous. I can't remember who it was. It's not commutative. That's like in communion with, like you group with, you associate with. That's not exactly the same thing. All right.